Hello dear friends, welcome my channel. Today's discussions is based on string theory and M theory. So friends, I am talking about formula of energy particles, non-relativistic limit, infinite momentum frames, momentum conservations, time dilations, open string interactions, and potential and continuum limit. So friends, a box of particles and the box may be moving slowly, but inside the box the particles may be moving with close to the speed of light. Can't use pure non-relativistic physics for all of these particles because they have relative motions which are up near the speed of light. So strictly speaking, the non-relativistic limit is a good thing to do when all of the particles are moving slowly. There another sense in which non-relativistic physics is an exact description of relativistic physics, so that goes back a long ways in particle physics. It was called the infinite momentum frame, called a light cone frame. So if you look up a light cone frame, you will see this described, but it's easy to get, and it easy the now E equals to summation root over p square c square plus m square into c to the power 4, and the energy is the sum of all particles of again square root of p and squared plus in squared. So E equals to summation E equals to, it can be written this way, E equals to root over p square plus m square. E equals to root over p square plus m square, and equals to root over p square x plus p square y plus p square z plus m square. Now we are boosting the hell out of the system along the z-axis until every single particle has huge momentum along the z-axis. Every single one of them, if there are any particle which is going backward on the z-axis, haven't boosted it enough, just boost it more until it's going forward with a large momentum. In that case of all pj's are very large, what happens to px, py and m when you boosting something? Nothing. That's the rest mass. We don't even speak about moving mass anymore. The rest mass and the components of momentum perpendicular to the boost don't change when you boost something. Now the big quantity is pz and px and m are kept fixed and much smaller than pz. So the appropriate thing to do here in talking the limit is expand it for large pz and expand it for this being small. A way to do that is to write this in the form square root of 1 plus, let's just call it p square x. So friends, E equals to Pz root over 1 plus P square x into P square y plus M square divided by P square z. Pz on the outside. Pz on the outside. If we brought the Pz inside, the square root it would have to be squared, it would be Pz square. Then it would cancel this Pz square. Here, what's the next step? Use the binomial expansion and binomial approximation to do exactly the same thing we did over here. This is now the small quantity, and this becomes, to summarize it, all the energy is the sum of all particles of Pz. So E equals to summation Pz plus summation P square, small p square, divided by 2 Pz plus summation M square divided by 2 Pz. Little p stands for Px and Py. Little p is square over twice big Pz square plus M square over twice big Pz. First observation, if we believe in momentum conservation, which we do in this class, if we believe in momentum conservation, then first of all, this is just the total momentum of the system. The first term here is the total z component of momentum. Going down the z-axis, it's huge, very large, but it's a constant that as various things go on in this system, the total momentum never changes. If you have a constant term in the energy which does not change in any way during the course of a constant additive things, adding it to the energy on subtracting it from the energy does not do anything. For example, if you added the electric charge to the energy, since electrical charge is conserved, and the only thing that's ever important in physics is differences of energy, you could just drop it or keep it, that does not matter. The same is true here. You have a conserved quantity which is conserved for other reasons. Then energy conservation's energy, of course, is also conserved, but Pz is conserved for other reasons. Here something never changes. You can just drop it. If you were to think of the energy as being the Hamiltonian of a system, it would make no difference whether you drop it or don't drop it, because it's a conserved quantity which never changes. So you can drop this, will make no differences the rest of the energy. Here is this thing here. Now first of all, notice that Pz is the denominator. And what does that mean? Why is the energy is so small in particular energy differences? For example, H for Hamiltonian equals to summation p square divided by some m square divided by 2pz. Differences depending on the state of motion in the xy plane, they will be teeny. Why are they teeny? Anybody know why are the energy difficult? It's useful to remember a bit of quantum mechanics, even though we don't need to be doing quantum mechanics. What is the meaning of the energy? The energy, of course, is quantum mechanics, is the same as the Hamiltonian. It is also in classical mechanics. But what's the meaning of the Hamiltonian in quantum mechanics? Do you remember your quantum mechanics? Quantum mechanics, in case of Hamiltonian, friends, must remember I del divided by del t equals to h. You can write this way: p square pz plus m square 2pz. The energy, but it's also associated with something else. It's also associated with time evolutions. All right, remember that it is the same as this. It is action as an operator. Hamiltonian is operator on a state that what it means to say energies are very small is that systems are changing very slowly. This is also true incidentally in classical mechanics. On just to point this out, there is quantum mechanics. If the energies of a system are very small, it means changes take place very slowly. The smaller the energy, if the energy scales with someone over pz, here it means that the larger the pz is, the slower things take place in the system. What's going on here? And very simple, it's time dilations. The more you boost the system up to higher momentum, so friends, time dilations in mathematically it can be written del t equals to del t0 divided by root over 1 minus v square by c square. This is time dilations. System up to higher momentum in your reference frame, the slower things take place. That interesting, but of course we have all the time in the world. Are a system moving, we can wait as long as we like to see things take place. If we are trying to make a theory of radioactive decay, sure, boosting it up will make the radioactive decay go slower, but we can rescale that out. We can say, instead of working on a scale of microseconds, we will work on a scale of million of years. nucleus decay, everything just has to be rescaled. So this 1 over pz, there's the total, this is 1 over pz, this is incidentally for the ith article, and we add them all up. So the fact that all the pz's get large incidentally, these pz's get large incidentally in fixed proportions, they all get large and fixed proportion, that said the energy got smaller, that a completely expected phenomenon. Apart from that, if we rescale only pz's, ignore the fact that they get big, or just rescale the evolution of the system, this Hamiltonian on this expression for energy really does look like the non-relativistic expression with respect to the motion in xy plane. For the motion in the xy plane, the energy is proportional to the square of the xy momentum, just as it is for the non-relativistic particles. But notice that the role of the mass of the particle in this non-relativistic analogy is not the rest mass, it's the momentum along the z-axis. What this means? What is mass is inertia, right? That go to do difficulty of deflecting. Saying is that the momentum along the z-axis is functioning as a kind of inertia with respect to forces in the perpendicular directions, and the whole thing is looking very much like, if we think of pz is a constant, then all this is non-relativistic formula for the energy of a two-dimensional particles. Now notice, we now have only two dimensions of this motion, and what is it, and what pz as being independent of the state of motion, at least a two-dimensional motion. So with respect to the two-dimensional analogy between relativistic and non-relativistic physics, it's an analogy between relativistic physics and two-dimensional motion, in which pz plays the role of the mass. And how about this object over here? It plays the role of binding energy. Does it have the right properties to be binding energy? Only thing about a binding energy is that it should be independent of the state of motion it. This does not depend on the two-dimensional motions. Now friends, we know E equals to, this equation I write, E equals to summation I p square divided by 2m plus pi. This is kind of interesting. It is incredibly useful in studying particle dynamics, and absolutely central to studying strings is that in a very precise and exact way, the motion of relativistic system, when it boosted up to enormously large momentum, behaves completely non-relativistic with respect to the motion in the plane perpendicular to the boost. For this reason, string theory is also a term described in terms of mathematics, which is the mathematics of non-relativistic string. A non-relativistic string is collection of point particles. A collection of point particles in some limit then which to let the points particles get more and continuous all moving non-relativistically. Non-relativistic physics, complicated relativistic physics. Non-infinite momentum frame, which these days is called the light cone frame, mostly because there's nothing to do with cones. Infinite momentum frame motions is non-relativistic. Non-relativistic. The motion of the string when it's boosted up may be described by not by a kind of non-relativistic quantum mechanics. We can think a particle as strings using the two-dimensional analogy with non-relativistic physics to explore those strings as if they were conventional non-relativistic math solaces, but something closer to rubber band, stretchable. They can move, they can flap, they can do all things that a rubber band, an ideal rubber band, can do. Mathematical description of two-dimensional rubber band which is moving around two in two dimensions. Let's take our rubber band to be an open rubber band. That means somebody took a scissor, cut it and opened it up. Let's begin with open strings. Open string as a collection of point particles which later on we will take limits as well. Let the mass of each points go to 0, and that's because we are going to have and the whole string E equals to m sub I summation x sub I whole square plus y sub I whole square divided by 2. X sub I dot and y sub I dot, x sub I dot whole square, y sub I dot whole square by 2. It as being a collection of a virtual infinity of point masses, it had better be that in taking the limit we let the mass of each point go to 0. Alright, the energy is going to proportional the kinetic energy. It will be the sum of all points of x sub I dot. How to do continuum limit? These points attracting each other. If they were attracting each other, they would just fly apart. They are forming a string. They are in additions to the point. We have to put in the little springs that connect them. So think of it as a chain of little balls. You see the spring, little ball, and the little spring. What is the potential energy between the points? The potential energy is a sum also over all neighboring pair. So E equals to m summation xi dot whole square divided by 2 plus k x sub I minus x sub I plus 1 divided by 2. This is Hooke's law. The points get denser and denser and denser more and more then. It's 0, so sigma is a 0 at this end, and at the other end we can arbitrarily say sigma is equal to pi. strings which go all the way around in a loop, it's to say they go from 0 to pi. That's all, but they go from 0 to pi, so the sum we take a little element, a point sigma. Sigma, we take this velocity, and I have chosen the masses to go appropriate way of in the dropping the mass here. By the time you finished, you can absorb the mass into something x dot whole square. X dot whole square is kinetic energy. So energy equations, energy is 0 to pi d sigma x dot whole square sigma divided by 2, and this can be written this way: del x by del sigma whole square. The energy of the string. If I wanted to write the Lagrangian, you all remember what a Lagrangian is. Energy is kinetic energy minus potential energy, and Hamiltonian is kinetic energy plus potential energy. So the Lagrangian is zero to pi d sigma. This is Lagrangian and this is Hamiltonian. Sigma is stretching of the string generalizations of this expression here for a system of particle which also has interaction between them. Whole object, it may be vibrating and doing things, but whole object is an object. We call it particle. Protons and neutrons have spin. They rotate threes, all sorts of internal motions in particles. We know there are interval motions of particles, internal motions of atoms, internal motions of quarks inside protons and neutrons. The best bet would be there are all sorts of internal motions in every particle. So the stringy vibrations and internal motions and so forth, that perhaps not perhaps but would add up to all the internal motions in the particle, all the internal energy in the particle. The internal energy would be the contributions to the energy from the potential stretching and from the relative motion of the different parts of the overall motion will separate out soon enough. The overall motion of the string, the center of mass of it, that would just be treated as the ball, as the position of all particle, but the relative stretching and relative vibrations, that internal energy. So when we calculate the internal energy of this particle, what should we relate it to? We should relate it not to the mass but it to the mass squared. I del T equals to capital H equals to summation p square divided by 2pz plus m sub I square divided by 2pz, this capital mass squared. In the corresponding, it is not an analogy, it's an exact statement about the properties of relativity, is a very precise mathematical statement which make now, but there was an exact sense in which part moving systems are completely relative and non-relative in the two-dimensional sense. The internal energy now respond to it would correspond not to the mass of the particle but to the mass square. So for a string at rest, think of a string which has no motion in the xy plane. All is doing is vibrating, and it has internal energy. That internal energy has to be identified with the square of the mass of the entire assembly of constituents of the string if the constituents of the string are adding up to something that we want to call the particle, then that particle has a mass squared, which is the sum of all the internal energies inside the particles. So friends, whatever we have learned all this topic. Formulas of energy particle, non-relativistic limit, infinite momentum frame, momentum conservation, time dilations, open string, interaction, potentials, continuum, limit.